So in Chapter 11, we're going to look at a slightly different type of hypothesis test. It's going to be very similar to the stuff that we've been doing, but it's actually going to be a slightly more realistic scenario. So in this section, we're going to be looking at a hypothesis test for the difference of means, so a difference between two different means. The idea that makes this a little bit more realistic is if you think back to, if you watched the previous video, we did an example about satisfaction of Toyota owners, basically whether they would recommend Toyota to a friend. And there was an arbitrary number. We said that Toyota wanted to use the results of this survey that they had done to try to make an argument that more than 65% of Toyota owners would recommend Toyota to a friend. And the question that I have for you is, why 65%? Where did that number come from? The idea is it was totally arbitrary. Why not just say 2/3 of Toyota owners? Make it 66, 0.6 repeating percent. Or why not just say 60% or some other number? Why did they pick 65? What's special about that number? And the answer is there is nothing special about that number. It was just an arbitrary decision. In this case, the number that we're going to be trying to test is going to be not an arbitrary number, but it's going to come from some actual experiment. We'll have two numbers to compare, basically. And so we won't have to run into the issue of making up an arbitrary number to compare something to. So oftentimes, this is used when people are actually running a real experiment. So these are often used, this type here. So these are often used in experiments where we want to compare the results of our experiment to some sort of control group. So where we want to compare our results to a control group. So the example that we'll see in just a minute will be taken from like medical field. This is where this type of thing might come up. Maybe we want to test to see whether this certain medication is effective at, controlling blood pressure or blood sugar or something like that. And so we'll administer the actual drug to some participants and a placebo, so some sort of sugar pill, something that they think they're taking a medicine, but there's actually no medicine in it, to a control group, and we'll compare the results. And we'll look at what is the average drop in, say we're doing blood pressure medication. What's the average drop in blood pressure from somebody that takes the medication compared to somebody that takes the placebo? And we can use that to decide whether or not the actual medication is effective at reducing blood pressure. So that's the example that we're going to do in a little bit. To do something like this, we need a little bit of notation, but it's ultimately going to follow the same 6-step procedure that we've talked about before. So our notation is as follows. Before we were trying to make a decision or asking a question about one single mean, mu. But now we need to have, excuse me, we need to have two of them. So I'm going to label them mu1 and mu2. We have two different means. These are the population means. These are the things that we're trying to draw some conclusion about. The reality is we'll never actually know the true values. All that we'll know are going to be x bar 1 and x bar 2, the two sample means. So we'll use these two sample means in hopes of drawing some conclusion about the two population means. We will also have two standard deviations, S1 and S2, and notice both of these are sample standard deviations because we're dealing with sample standard deviations with S's. that means that this problem is going to involve using a t-distribution rather than a normal distribution. So just remember, S and T always go together. Every other type of hypothesis test will use a normal distribution. But if you're dealing with S, you're also going to be dealing with T. Okay, so sample standard deviations. And we also have potentially two different sample sizes. Our two groups don't have to have the same number of participants. So the number of people that take the placebo versus the number of people that take the actual medication, they can be different numbers. So we're going to have two different sample sizes. So here's all of the new notation that we're going to have. The conditions that we're going to need to meet for this to run, they're similar to the ones that we've talked about in the past few scenarios. We need simple random samples. So if we don't take good samples and get good data, then the results are going to be worthless regardless. So simple random samples. The second requirement is that we're going to need independence of our two samples and of the two experiments. So basically, what I mean by this is the result of the people that take the medication shouldn't affect the result of the people that take the placebo. There shouldn't be any sort of cross-contamination, so to speak. There should be no interdependence between the two groups where the result of one affects the result of the others. And lastly, these two simple random samples that we've taken for our two different groups that we're going to be looking at both need to be large. So both samples need to be large. And greater than 30 as before. That way our sampling distribution could potentially follow a normal distribution. The other way that if we have small samples that we could wind up still being able to follow this normal distribution, so both samples must be large, we'll get a normal distribution, or if we draw the samples from populations that are normally distributed to begin with, we'll also be able to be assured that our results will follow the normal distribution that we're hoping. I know this is all kind of confusing, so let me just write this down here. Or the populations must be normally distributed. So the populations that we're drawing our samples from, if they're normally distributed, it doesn't matter how large they are. That's the gist of what this is saying. So if these three conditions are true, then we're good to go. Again, it's confusing. The idea is that these sampling distributions will be normal distributions relative to the standard deviation of the population of sigma. But again, because we're using S, that's what transforms what would be normal distributions relative to sigma into t distributions relative to S. So we're still going to be using t distributions, even though I'm using the word normal distribution here. So just keep that in mind. Okay, our procedure is the exact same procedure that we've gotten used to, same 6 steps, and we're going to start going through these slightly more quickly because they're really the same 6 steps. Hopefully you're starting to get used to them, and I'll highlight where the differences occur. So the first step is to state the null and alternate hypothesis. And as before, our null hypothesis will denote with H sub 0. The alternate hypothesis will denote with H1. Again, these are just labels. Something I want to warn you about, a mistake that I often see is people putting equal signs here. These aren't equal signs. These are just labels, and what's going to be written after it is an actual equation, something that will involve an equal sign. Our null hypothesis is going to be that the two results, mu1 and mu2, are the same. And the alternate hypothesis will take one of several forms, either that mu1 is greater than mu2, that mu1 is less than mu2, or simply that mu1 is not equal to mu2. So those are the 3 possible cases. One thing that can be kind of nice is to it's kind of hard to tell right now which one of these is the left-handed or left-tailed and which one of them is right-tailed. This one's clearly the two-tailed case, the not equal sign, but which one of these is left-tailed, which one of these is right-tailed? Which one am I sort of using as the reference? And so I want to make it a little easier to spot which is which. All I'm going to do is for each of these inequalities here in the alternate hypothesis, I'm going to subtract mu2 from both sides of the equation. So on the left, I'll have mu1 minus mu2, and on the right-hand side, I'll have mu2 minus itself, which will leave 0, and we'll have mu1 minus mu2 greater than 0. So that's the equivalent statement to the one that's right there. This one says mu1 minus mu2 will be less than 0, and this one will say mu1 minus mu2 is not equal to 0. So all we're saying is if mu1 is in fact bigger than mu2, then when I take mu1 and subtract off mu2, when I take a large number and subtract a smaller number, I will get something that is positive, and that's what this is showing. Whereas if mu1 is smaller than mu2, I take a small number and subtract a larger number, a smaller number minus a larger number, I will get something that's negative, and that's what this is showing. And then this one again just shows that it's not equal to 0. This second form where I've written stuff down in this second line will be maybe a slightly easier thing to use because these are actually how the mu1 and mu2 will show up in the formulas later on in the problem. So this is kind of going to be the idea of it'll show up in this form. We're looking at a difference of two means, which again is the whole title of this section. We're looking at the hypothesis test for the difference of two means. And that's what we're looking at when we write things in this particular format as a difference of two means. So now it's more clear because we've got just a number sitting on one side. This is the greater than some number, so this is the right-tailed case. This is the left-tailed case, and this is the two-tailed case. Because we are greater than some given number, so to the right, less than some given number, so to the left. Oh, come on. It's okay. And that's what we're looking at now. Okay, so this step is slightly different. We have stated our null and alternate hypothesis. Time for step 2. Step 2 is still defining what we're going to consider weird. And we have two different ways to do that, as in all of these different examples. If we're doing the p-value method versus the critical value method, we just need to specify the significance level if we're doing the p-value method, which is alpha, it's given in the problem. And if we're doing the critical value method, we need to find the critical value. And again, the critical value here is a t-score. It takes the form of either t sub alpha, negative t sub alpha, or plus or minus t sub alpha over 2, depending on whether we're dealing with the right-tailed, left-tailed, or two-tailed case. And it will depend, because we're using a t-score, it will depend not only on the value of alpha, so for the given alpha, and the given degrees of freedom, which again, just to remind you, is n minus 1, one less than our sample size. We'll find that the same way that we have in the past using table A3. So this will be table A3 is where we go to find this critical value. This third step is the main difference. It's where we compute the test statistic, but this formula looks different from the test statistics that we've done before. So it's a t-score. And again, I'm going to write it out and then we'll take a look at what how this compares to the other ones that we've done. So it's going to be x1 bar minus x2 bar. From that, I'm going to put that in parentheses, subtract from that the difference in the means, mu1 minus mu2. Then I'm going to take the whole thing and I'm going to divide it by the standard error, which in this case needs to combine both pieces of data. So it's going to be s1 squared over n1 plus s2 squared over n2. the whole thing square rooted. So it still has the same three pieces. These are our two sample means. So this is going to have to do with the evidence from our experiment. This has to do with the null hypothesis. And notice our null hypothesis, if I get this all on the same page, our null hypothesis is that mu1 is equal to mu2. So if I were to rewrite this in the same way that we rewrote all these alternate hypotheses down here, I would write this as mu1 minus mu2 equals 0. So two ways to say the same thing, right? I can either tell you that the two means are the same, that the first one is equal to the second one, or I could tell you that the difference between them is 0. There is no difference between them. That's the same as saying they're the same thing. So two different ways to phrase it. What this tells me, though, is that mu1 minus mu2, which is what I've got right here, it's presumed to be 0. So this whole part, the book doesn't even bother to write. It just assumes that that's 0 and it leaves this out. But I'm writing it so we see the same three pieces. It's always the evidence minus the null hypothesis, all of that over this thing here, which is our standard error. So this is the standard error. So it's the same three components that go into our test statistic. So I just want to write that all out for you. Again, these formulas get increasingly complicated. This is one of the pieces that when we do one of these problems on the calculator, it'll spit out this number for us. So we don't necessarily have to try to plug in manually into our calculator all these individual numbers. So we'll take a look at that in a minute. The rest of the problem is pretty much identical to what we've been doing. In step 4, if we're doing the critical value method, we can skip this step because I already have my two t-scores to compare. I have my test statistic. I have my test statistic that we computed in step 3. I have my critical value from step 2. I have the two t-scores that I can compare, so I don't need to do this step. But if we're doing the p-value method, I only have one of the two areas. I have the significance level, again from step 2, alpha. That's one of the areas, and I need to compare it to the area associated with this test statistic, the area associated with our actual evidence. And that's the p-value. So we need to find the p-value, which is, again, area to the extreme of the test statistic. And again, I've mentioned this in the previous videos, but let me make it extra explicit here in this one. So this is an important side note. I've said it, but let me make it extra explicit here. The p-value is the probability of getting the results that we actually got. So the p-value tells us how likely, how weird is our evidence. So it tells us the probability of getting the results that we actually got. And by results, I mean the stuff that we're using for our evidence, the values of x bar in this case. By chance. So it tells us the probability that this happened by chance under the assumption that the null hypothesis is true. So this is really why the hypothesis test boils down to a weirdness test. We define what we're going to consider weird, we look at our actual evidence, and we compute the p-value to see how weird is our evidence. And if it meets the cutoff of what we consider weird, then it's weird. And we say we're getting a weird result. Maybe we made some bad assumptions that are leading to these weird results. So that's kind of the idea. Step number 5, same as before. Determine if our result is weird. Come on, pen. Again, if we're doing the critical value method, I compare those to t-scores. So it's weird if the test statistic t is more extreme than the critical value, which is either t sub alpha, negative t sub alpha, or plus or minus t sub alpha over 2. And in the p-value method, our result is weird if the p-value, the probability of getting our result, so it's weird if the p-value, which is again the probability of getting the results that we got, is less than the cutoff of what we consider weird, which is alpha. And if our result's weird, we're going to say we must have made a bad assumption. Let's reject the assumption we made. Let's reject the null hypothesis. And step 6, state our conclusions, again in plain English. Okay. So here are our steps all in one place. It's the same 6 steps that we've been doing. The major differences are we kind of had to set up the null and alternate hypothesis a little bit differently now, but they're actually easier to determine in this case than they are in the problems from chapter 9. So again, this is the first section from chapter 11. These, I think, are easier to determine. Setting up this null and alternate hypothesis are easier now because we aren't comparing stuff to some magic arbitrary number. We have an actual 2 sets of numbers to compare. And this is the other main difference. We have a new formula for the test statistics. So really, these are the only differences. This we've done before, this we've done before, this we've done before, this we've done before. The rest is the same. So let's do an example. Okay. So here is my example. I'm going off the screen here. I don't know why it's not letting me scroll. Okay. Good enough. Whatever, we'll just work with this. So here's our example. Again, I mentioned it was going to be a medication problem. So we're going to look at new blood pressure medication. So we want to test a new blood pressure medication. To see if it is effective at reducing blood pressure. And there's 2 types of blood pressure. There's diastolic and systolic. Those of you that are going into some medical related field probably know more about it than I do. So let's just pick one of them. Let's say that in this case, we're trying to reduce systolic pressure. So systolic blood pressure. Okay. So our participants in this study, we're going to have 2 different groups of people to test this blood pressure medication. And so we'll say one group of maybe, I don't know, let's say 70 people. I think that's what I've got in my example here. So one group of 70 randomly selected participants they take the drug. So one group of 70 randomly selected people takes the drug. while 85 randomly selected people take a placebo. So they think they're taking a drug, but it has no actual medical effects other than the placebo effect. They think they're taking a drug. And the results are as follows. The group that takes the drug sees a drop of 16 mmHg, millimeters mercury. This is just the units that they measure blood pressure in. So 16 millimeters mercury with a standard deviation of, let's say, I'm trying to get my numbers here, 11, standard deviation of 11 millimeters mercury, while the group taking the placebo sees a drop of 12 millimeters mercury with a standard deviation of 6. Okay. So, see what we've written here in this short novel. We're testing a new blood pressure medication to see if it's effective at reducing systolic blood pressure. There's two groups of people. So one group of 70 randomly selected people takes the drug. 85 randomly selected people take the placebo. The group that takes the drug sees a drop in their blood pressure of 16 millimeters mercury with a standard deviation of 11. And the group taking the placebo sees a drop of 12 millimeters mercury with a standard deviation of 6. We want to know, is the drug effective at reducing blood pressure? Is the drug helping, essentially? So, does the drug help reduce blood pressure at a significance level of, let's pick a new number. We've done a bunch with 0.05. Let's do 0.01. Okay, so there is our question. We want to know whether this drop that we see, that looking at the results, the people that took the drug saw a bigger drop in their blood pressure than the people that didn't take the drug. Is that a fluke? Is that random luck? What we're going to do is test to see how likely that difference is to just be by chance. Maybe it is a fluke. Maybe we just got lucky in the way that we selected people and just happened to find a group where the people that took the drug saw a larger drop, just totally by chance. Their placebo effect was bigger. So if it turns out that that's really unlikely to have happened by chance, if it's really unlikely to have been a fluke, then we'll say, okay, we don't think it was a fluke. We think it was because the blood pressure medication actually helps. But if we see that there's a good possibility that it was a fluke, then we'll say we don't have strong enough evidence to show that this medication is effective. It could have totally been a fluke, the results that we're getting. That is the whole idea of this hypothesis test. So let's go down and actually go through the steps. So step number 1 in our procedure, we've got, again, going through our conditions. Our two groups were both random samples. They're both large, and we have them so they're totally independent of one another. The results of each individual has no bearing on the results of any other individual. So we meet all the conditions that we need in this case. So let's state the null and alternate hypothesis. And again, the null hypothesis is always, so in math, the word null basically means nothing. So that's kind of the idea that it is going to mean here. The null hypothesis is the idea that nothing happened. The drug did nothing. It's not effective. There's no difference between taking the drug and not taking the drug. That's what I mean when I say it kind of goes along with the word no. Nothing, no difference. That's what we're talking about. So the null hypothesis is always, we think the two outcomes are going to be the same. The reality is your average drop in blood pressure if you take the drug is the exact same as if you just take a placebo. The drug's not effective, essentially, is what this is saying. You see the same results either way. So again, we can rewrite that as mu1 minus mu2 equals 0. There's no difference whether you take the drug or not. The alternate hypothesis will take one of these various forms, and we kind of get to pick. I want to do one that turns out to be left-tailed. We've done a bunch of right-tailed hypotheses. Let's do one that is left-tailed. So the way that we're going to do this is we have to pick which group we're going to call which. And the way that I want to do this is by setting up a little table. So I want to think about, I'm going to draw a table over here to keep track of things. The values that we need to know are going to be the values of x bar, the values of S, the standard deviations, the sample sizes, and ultimately we're trying to draw some conclusion about mu. And so we'll have group 1 and group 2. There we go. And I want to pick which group is the group that takes the drug and which group is the group that takes the placebo. I'm going to have it set up so that this is the placebo group and this is the actual drug group. So those are going to be the values. In a minute, we'll see that this should wind up giving us something that's left-tailed instead of right-tailed, and we can talk about exactly why that worked out that way. So basically, I need to specify what x1 bar is, what s1 is, what n1 is, and mu1 is the thing we're trying to find. We'll never actually know the true value of mu1. It's what we're trying to draw a conclusion about. What is the average drop if all people took a placebo that claimed to lower their blood pressure? And similarly, we'll have the second group over here with all of the subscripts of 2 instead of 1. So I want to specify all these values. And if we go through the two groups, the placebo group, they saw a drop of 12 in their blood pressure, and the standard deviation was 6. And there were 85 total people in that group. For the group that took the drug, they saw a drop of 16 millimeters mercury. Their standard deviation was 11, and there were 70 of those people. And again, this is something we'll never know. So here are my two values. The way that I know this is going to wind up being left-tailed is because the assumption is, in this case, we want to know basically, our evidence shows that the people that took the drug, they saw a larger drop than the people that didn't. So basically what we're saying is, comparing mu1 and mu2, it looks like it should go this direction. Mu1 should be less than mu2. Mu1 is the drop that I would expect to be associated with the placebo group, because that's group 1. Mu2 is the drop associated with the people that took the drug. Our evidence shows that group 2 had a bigger drop than group 1, that this number should be bigger than this number. And that's how we've got it set up. And if we rewrite this doing subtraction, we get mu1 minus mu2. Again, keeping in mind that this number's larger, this number's smaller. I take a small number, subtract a large number, and I will get something that's negative, less than 0. So this is left-tailed. If I wanted this thing to be right-tailed, all I would have had to do is switch which one I called group 1 and which one I called group 2. And we would have gotten a totally identical results at the end of the day. All that would have changed is instead of, in this problem as we go through it, all of our computations are going to take place in the left tail. if I'd switched the names of the two groups, all my computations would take place in the right tail. So if you're more comfortable doing a right-tailed hypothesis, the nice thing is we can set these up to be either tail. You can force it to be in the tail that you want by just thinking about it a little bit ahead of time. So maybe we'll talk about that more on some more examples after you've practiced a few on your own. Okay, so there's our null and alternate hypothesis. I would highly recommend doing this table that I've done here. It'll make it really easy down the line to just be able to plug in numbers into our formulas. We've done a bunch of these problems doing both the critical value method and the p-value method. Let's just do one this time. So let's just do just the p-value method. So I want to do just the p-value method. That means to define weird, I just need to know the significance level, and it was just given in the problem, alpha equals 0.01. We're going to consider something weird if it would happen by chance less than 1% of the time. So that makes it so this is really easy. Again, we're only doing the p-value. I can put this over here in the side margins here, only p-value. Again, you can do this with the critical value method, but we don't need to do both. The p-value is the one that actually gets used more. I want to do that one here. Step number 3. Here's where we need our test statistic. Oops. In fact, actually, before we do the test statistic, let's just draw our picture just so we can get some practice with that as well. So what is the scenario that we're looking at? We have a scenario that looks like this. Here is our curve. It is the curve of all the possible differences between x1 and x2 bars. We are assuming that the average difference, according to our null hypothesis, is that we've got mu1 minus mu2 equals 0, sitting here in the middle. 0 is the middle. We've defined weird to be, in this case, the most extreme 1%. We know that the side that we're interested in is the left tail based on the way that we've set stuff up. So the region that we're going to consider weird is this little tiny region right here. So this is our weird region, the most extreme 1% of the area. So if I kind of chop this up into two pieces, here's our not weird side, and here's our weird side. And we want to find out where our result falls. If it falls in here, it'll be considered weird. If it falls over here, it's not weird. So let's see where it actually falls. So step number 3. Here's where we find that test statistic. So we wrote the formula earlier. Our test statistic is x1 bar minus x2 bar minus the difference between the mu's, so mu1 minus mu2. We already have assumed that that's going to be 0 according to our null hypothesis, and we're dividing by the square root of s1 squared over n1 plus s2 squared over n2. So that's what it looks like. If we plug in our actual numbers, it's kind of nice. Let me zoom out just enough to see our table. We can plug in now all of these numbers directly from the table. They're all written down. We've already decided what each one is. So if we were careful when we made our table, this can just be kind of mindlessly plugged into the formula now. So my x1 and my x2, I'm going to get 12 minus 16 on top, again, minus 0. And in the denominator, we've got S1 was 6, so I'm going to have 6 squared over 85, plus the other one was 11, 11 squared over 70. And plugging this in to our calculator, I get about negative 2.727-ish, if I do it to 3 decimals. It makes sense. It should be negative. This number we get up here should be negative. It's a smaller number minus a larger number. We get -4 on top. This number down here has to be positive. We're taking a square root of a big squared bunch of squared numbers that are all positive. The overall result should be negative, which makes sense. If 0 is in the middle, the negative number should be over on the left. So we want to know, is this number, -2.727, is it in this region or is it over here? We know it's pretty far to the left. Is it far enough to get all the way to the region that we consider weird? We don't know that yet because we haven't been doing the critical value method. I never found the t-score right here. We would find the t-score here if we were doing the critical value method, but we're not. So I need to find the area associated with this. Is the area associated with this going to be less than 1%? So that is our next step, step 4. So we want to find the p-value. The p-value is, again, the area, in this case, to the left of t equals -2.727. So I'm going to go look at table A3. Let me insert it real quickly here. Oops. Get all my stuff in order. There we go. So here's the table. Oops, I also got a page I did not want. Let me delete that one. Only want this table. So let me move that over here. And move everything around. Okay. Phew. Okay, so I want to use this table. The first thing that we need to do, going back to our problem, is to figure out what our degrees of freedom was. And this is going to be a little bit tricky because I need to figure out the area. I want to use this table. I need to know which row to use. So note, our degrees of freedom, we normally take n and subtract 1. But in this case, there's two different n's. There's n1 and n2. So which do we use? We don't have an n. We need to use the more conservative one. So again, we're always going to play conservative. I'm going to use the smaller of whatever my two sample sizes was. So in this case, use the smaller n, which in our case is n2, which was 70. So I'm going to use 70. So for us, our degrees of freedom is going to be n2 minus 1, which is 70 minus 1, which is 69. Going to my table, I'm supposed to use row 69. There is no row 69, so what do? Again, we have to round down, and I'm going to use the row labeled 60. So in our table, for this problem, this is the only row that I'm allowed to use. Whoa. Just that one row, row 60. And so I'm looking for 2.727. Ours was negative because we were dealing with the left tail, but notice in this case, the drawing shows the area in the right tail. So we need to use that symmetry idea that we've talked about this semester. I'm not going to be able to find areas in the left tail that are associated with the negative numbers. All of these numbers in here are all positive t-scores. So instead, I'm going to come over here and look at the mirror image. So instead of looking up t equals -2.72, I'm going to look up t equals positive 2.72. I'm going to look through this list and try to find that number. It's not in here, but it would be right there. There would be 2.727. So it's between that number and that number. And those two numbers are associated with those two areas. And that's what the p-value is. These are the two areas that I'm interested in. So coming back up to here, I can't find the p-value exactly. Let me do it off to the side. But I do know that our t equals -2.727 will be between these two other t-scores that I found down here. So 2.660, technically that goes over here, negative 2.660, and negative 2.915. Yes, 2.915. So let me move this whole thing over here a little bit. Now it's taking the 2 with it. Let me delete that piece. Rewrite what we've got over here. So negative 2.9. Okay, so our t-scores between these two t-scores, meaning the area associated with it, which is the p-value, will be between the areas associated with these two t-scores, which were respectively 0.0025 and 0.005. So I don't know exactly what the p-value is, but I've now ballparked it to be in that range. So let's zoom out. I just want to make it totally clear, go through this one more time. We're only allowed to use row 60. That had to do with the degrees of freedom that we found. Our sample size was 70. That was the smaller sample size. We subtracted 1 to get 69. There was no row 69, so we rounded all the way down to 60 and got this number here. It said this is the only row that we're allowed to use. I searched through this row looking for 2.727, the positive version, just because we're dealing with the right tail and not the left tail in this table. This table only does right tails. And we decided it was between these two numbers right here, and therefore the area associated with this particular t-score must be between the areas associated with those two t-scores. And there's the two areas that we wound up finding. So if you're good with that, I'm going to adjust this piece over here. Come on, I just want to delete just this piece. All right. Let me remove this just so nope. Oh, come on now. Let's delete that, then I can delete this whole thing. Okay. Yeesh. Okay, so we found our ballpark for our p-value. It's between those two numbers. What do we do now? We need to decide if our result is weird. So our result is weird. And it's weird because our p-value, which I don't know exactly, I know it's less than 0.005 according to this relationship right here. It's less than 0.005, which is definitely less than 0.01. Notice that there's one less 0 in this term, which was our cutoff for what we would consider weird. So our result is weird. That means we are going to reject the null hypothesis. Coming back up to our picture, we found out that our result must have been somewhere in here because it had a smaller area associated with it. Our p-value wound up being less than 0.005. So something like that. Our result fell into that weird region. So we've said our result is weird. It's only weird under the assumption that the null hypothesis is true. So let's say maybe that was a bad assumption to make. Let's reject the null hypothesis. If we think the null hypothesis was wrong, what we will look at instead is our alternate hypothesis. We do, in fact, think that mu1 is less than mu2, that the blood pressure drop of people that took a placebo is less than the blood pressure drop of people that took the actual drug. So what does that tell us? If the placebo was less effective than the drug, the evidence strongly suggests the drug is effective. Is in fact more effective than a placebo. So more effective than placebo at lowering systolic blood pressure. again, notice this last sentence, our conclusion, has no statistics jargon. It does have some medical jargon, systolic, placebo, etc. But it doesn't say anything about null hypotheses. It doesn't say anything about significance levels or p-values or anything like that. It's just a plain English sentence. The evidence strongly suggests the drug is more effective than placebo at lowering systolic blood pressure. That is our conclusion. How do we do this one on the calculator? Same thing we've been doing. We'll hit the stat button, go over to our list of tests, and now we're going to look for the right kind of test. In this case, we are looking at two separate samples. We're using a t-distribution, and so if we go through all of the options here, the correct option to use should be a two-sample, so two-samp t test. That's what we're doing, a two-samp t-test. And when we do that two-samp t-test, it'll ask for all of the numbers that we initially put into that table. So it'll ask for x1 bar, sx1, n1, so it's asking for all of these. It'll ask for x2 bar, sx2, and n2. Let me actually write these as subscripts. Good enough. And then it'll ask for the form of the alternate hypothesis of which way mu1 is relative to mu2. So going and filling all of these numbers in, which we just have from our table from earlier, which hopefully we can see. Ooh, that's going to be tiny. See if you can see them all. So the x1, all the group 1, all the 1 subscripts were 12, 6, and 85. So that was 12, 6, 85, and the other group, it dropped by 16. The standard deviation was 11, and there were 70 individuals, if I remember correctly. And we just figured out that mu1 was less than mu2. That was the form of our alternate hypothesis. When it asks if we want to pool our data, keep that on no. We do not want to pool our data for this. So enter all those numbers in, 12, 6, 85, 16, 11, and 70. And hit calculate. It'll spit out some stuff that we already found. It'll give us our test statistic, which is negative 2.7266455533. So it gives us the test statistic that we found back in step 3, and it also gives us the p-value. So our p-value is equal to 0.003766945. So it does better than what we could do. All we could do was ballpark it and say we know the p-value is less than 0.005, bigger than 0.0025, and we found exactly how small it is here. So again, it gives us the results of step 3 and step 4. That's what the calculator will give us. We still have to come up with all the conclusions ourselves, figure out how to utilize these numbers and interpret what they mean, but it gives us those values. It does step 3 and 4 for us. Okay, so we'll get some more practice, do some more of these in the next few sections, and I'll hopefully post another video soon.